I don't think there's any question that's greater than are we alone? And how does life arise? Where are habitable environments in the solar system? Most of the early theories about how life arose on the Earth were that it arose in the shallow seas on the Earth. There was this famous experiment done. I mean, it was actually done in 1952, but the ideas that that experiment spawned stayed with us for decades and decades. When I was a graduate student in, around 1980, working in Carl Sagan's lab, this was the thing that people believed that the early Earth's atmosphere, which was at that time when these experiments were done. This is Stanley Miller. Along with Harold Urey, he's the person that did this famous experiment that showed if you take the early Earth's atmosphere, and at that time they thought it was methane, a little bit of nitrogen, maybe some ammonia, um, and zapped it with electricity or some type of energy, all these amino acids magically formed, and those amino acids became primitive bacteria, which evolved into life. So that was it was all very hand waving. We didn't understand it at all. But when I was a graduate student at Cornell, this is an image I took. This is Ed Salpeter. He's not as famous as Carl Sagan was, but he was a great astrophysicist. He's passed on. I mean, all these people have passed on, but he was a physicist, and I took a course in stellar structure with him. Totally amazing. And I was, working with Carl Sagan. Started out working with him and did some research with him. But I just wanted to give a little nod to Bishan Kari, who was we used to call him a cooker. He had this lab, just like Stanley Miller's lab, and he would do all these experiments where you take a primitive Earth atmosphere, you zap it with radiation, and this stuff that Carl actually called it tholin, or an intractable polymer. And Bishan was trying to do the chemistry of it and see what it was. It was a bunch of amino acids and complex hydrocarbons. So this was kind of what we thought, that these complex hydrocarbons, for example, here is a picture of artist conception. I think this is from Smithsonian Magazine, of what the early Earth looked like, where you had all these shallow seas, and these are actually things called stromatolites. These are primitive bacterial mats. And the early Earth had some volcanism. There's also a lot of cratering on the early Earth, so there was hot heat, there was a lot of energy coming into the system, and this was how life formed. Okay. Well, in the early 80s, we started to realize that there were oceans underneath a lot of these planets and moons that we were looking at. And at the same time, there was this theory, and this is kind of what most people believe, that in these thermal vents in the Earth's oceans, and these tend to occur along tectonic plates, where the Earth's crust moved. If you look at uh, them, they are teeming with life. Here's I think those are shrimp and crabs, but there's also primitive bacteria that are teeming in these thermal vents. Sometimes they're called smokers. And the thing that is so interesting about them, if you look at the tree of life, okay, if you look at the base of it, these primitive bacteria seem to be at the base of the origin of life. This is called, and I'm not a biologist, so I'm just, copy this out of Wikipedia. Last universal common ancestor, the Luca, probably lived in the high temperature water of deep sea vents near ocean floor magma flows about 4 billion years ago. Okay. And from these primitive bacteria, or even pre-bacteria, all the life that we know on Earth arose. So this is kind of what we believe now. I mean, I would say it's a consensus view. Okay. So the early search that NASA was doing, that we were doing for habitable environments where life could arise, has been to search for liquid water, because life as we know it needs liquid water. Okay. So where did we look? We looked on Mars. Okay. And on Earth, wherever you see water, it's teeming with life. Okay. So let's look on Mars. I'm not going to go over the whole history of this. I actually went back and read Percival Lowell's book. I think I still have it in my office. Okay. Um, and the book is just, it's just kind of wrong. This thing about the poles of Mars and they get green in the springtime and Martians bring down water, which makes plants get green. Even back then we knew that that was unlikely because we knew that Mars had a very thin atmosphere, but still there was this mystique about Mars and a lot of science fiction literature, Podkayne of Mars or the Martian Chronicles was written about Mars. Okay, so and also at the same time, a lot of scientists had labs where they were growing stuff under what might be Martian conditions. Okay, so I can remember, old enough to remember Mariner 4 when it flew by Mars and we got really the first pictures of Mars close up. So disappointed to see this. Okay, I had this fantasy that, maybe at the equator it was balmy enough to have plants or, some type of life. But probably some of you remember when Mariner 4 went by Mars, it showed it to be more like the moon. It was heavily cratered. Now, this wasn't what all of Mars looked like, though. Later explorers, right now we have the Mars Reconnaissance Orbiter around Mars, and I'll get also to the rovers. We had a more realistic view of Mars, that in the past, Mars did have not only flowing water, but it also had standing water. Now, how do we know it had standing water? And the possibility of early primitive life. Because if you look on the surface of Mars, this is the Mars 2020, and that's our little helicopter, Ingenuity. And if you look at some of these rocks, some of them really look like they have episodic episodes of standing water where sedimentary rocks had formed. Okay, and if you actually look at an early Mars, this is what Mars looks like today. But if you go back in time to the early part of Mars, the solar system is about 4.6 billion years old. So we're talking about 3 billion years ago, 4 billion years ago. And geologists have seen what look like coastlines in the northern part of Mars. If you kind of take it back, this is what Mars may have looked like early in its history. It had oceans, a much thicker atmosphere because the planet is smaller than the Earth. It's easier for gravitational escape of gases in the atmosphere. So it has an atmosphere maybe about 1/100th that of the Earth today. Okay, and that's why Lowell should have known there couldn't have been people and plants there, but made a good story. Okay, actually, if you read his book, if you have a chance to read Percival Lowell's book, it really is more. I would say it's more of a early book about warning about ecological disaster on Earth because he did get that right. He realized that Earth could maybe end up the same way, and we have to preserve. We have more deserts and stuff like that. So he was one of the earliest scientists that understood the importance of preserving our environment. Okay, so let's move on to, I have a couple pictures here of the Martian surface. This is actually, I think this is a Pathfinder. So you can see there's a lot of rocks there. This is Death Valley, and this is JPL. We like to go out to Death Valley, and I actually was there for the Dark Sky Festival. I don't know if anyone was there from this astronomy club, but I was out there giving a talk about uh, about how we test things in Death Valley. Here's a helicopter, and it is so uncannily like, oops, like the surface of Mars. This is where we test all our stuff. Okay, all right. So I do want to move on to the main topic of this talk, getting into these new ideas about how life formed in oceans, subsurface oceans, on moons, icy moons, and maybe even on planets or demoted planets. So let's talk about Jupiter. Now, this is an astronomy club, so I don't have to go over this, but just to kind of review. and maybe dispel some scientific misconceptions. Galileo did espouse the heliocentric view of the solar system. But if you go back into history, and by the way, Carl Sagan's book Cosmos really goes over this really well. The early Greeks were also heliocentric. People like Aristarchus and Eratosthenes, who measured the size of the Earth to 50 miles. I mean, they did amazing experimental stuff, and they were heliocentric. But in Europe during the Dark Ages, and I'm not a historian of science, so this may be naive if there are any historians of science here, but things kind of went backwards. The Arabs did well. Of course, the Greeks, the more idealists, the Pythagorean, the Ptolemaic system was geocentric. But so Galileo wasn't the first one, but he certainly ran into trouble with the Catholic Church. These are some images, some notes from his observing notebook, Sidereus Nuncius. And one of my colleagues, Guy Consolmagno, there was a really nice profile of him in the New York Times about 2 or 3 months ago. Anyway, he was in one of my classes at MIT, and we stayed in contact and stuff like that. And he was asked to be the curator of the meteorite collection at Castel Gandolfo, which is the Pope's summer residence, and a bunch of Cassini scientists. Before I worked on Europa Clipper, I was working on mainly on Cassini. This is the spacecraft that went to Saturn and did amazing things there. And we had a meeting in Rome because we had scientists from Rome we were collaborating with, and he invited us up to Castle Gandolfo. He later became, at that time, he was curator of the meteorite collection, but he actually became the director of the Vatican Observatory. But he took us, to see the collection, and then he pulled out the first edition of Sidereus Nuncius, and this is in the Pope's library. Okay, pulled it out, and we were allowed to like hold it and touch it. I mean, there were only a few scientists there, and then as I was holding it, I realized this was probably the same copy that his inquisitors held while they, questioned him and stuff. So that was kind of a high point. Anyway, getting on to um, some basic facts about Europa. And, again, I don't have to even go over this. I mean, this is one of the things about, talking to astronomy groups. I mean, a lot of the stuff you probably know better than I do about the sizes and stuff. But here it is in comparison with the moon and the Earth. It's 5 times the distance from the sun, so it only gets about 4% of the radiation that we get, the solar energy. It orbits the sun about every 11 or 12 years. It orbits around Jupiter in 3.5 days. Let's see, the density is about 3, which means there's some rock inside of it. Even though it's ice, there's some rock in there, and it has a very thin atmosphere. Okay, so that's Europa. But here's the most amazing thing about it. This was the thing that the Galileo spacecraft, not the man, the spacecraft found. Okay. And actually, Corey Cochran did the visuals on this. He's one of the scientists working on the mission with me. And he's a magnetometer expert. And if you take the magnetic field of Jupiter, and now remember, Jupiter rotates about every 10 hours on its axis. So this magnetic field gets kind of swept around Europa. And what the Galileo spacecraft measured was an induced magnetic field on Europa. Now, this is Faraday induction. If you took a physics class, you know that if you have a moving magnetic field going through a conductor, you also have a magnetic field in that conductor. So we knew there had to be something in there. And the most likely thing is a liquid ocean. Okay. So this is what we think the interior of Europa looks like now. We'll talk about the crust and this weird geology on the surface, but the most likely explanation of that induced magnetic field is that there's liquid water. Okay. And then there's some rock because the density is 3, so there's got to be some rock in there. This is an official, I think, NASA image, and it shows a metallic core. I'm skeptical about that. I'm not sure. I mean, metal is kind of it's a refractory material and likes to condense under higher heat in the inner solar system. So I don't know how you get all that metal out there, but um, there could be a metal core, but I don't think that's been proven at all. Okay, so that's what we think the interior of Europa looks like. Now, there's another thing about Europa that's really interesting. Remember, I showed those little smokers in the Earth's oceans. Well, how would you get that heat on Europa because it doesn't have plate tectonics and it's really far from the sun, and it only gets like 4% of the sun that we get. But the orbit of Europa is not totally circular. It's eccentric. So what happens? Let's see if I can play this again. What happens as it is in its apogee? Okay, I don't have to define that. Okay, and when it's in its apogee, it's actually not as the tidal forces are not as great. Okay, so it flexes in and out. When it's close, it squashes. When it's in its perigee, and it goes into apogee. So if you see this, see it flexes in and out by the tidal forces. And of course, the tidal forces of Jupiter are huge. So it dissipates that mechanical heat as, or that mechanical energy is heat. Okay, so that's how we get the heat on Europa. All right. Now let's look at kind of, this is an artist rendition. We're not sure this is what it looks like, but this is what we think it looks like. And this is why we're going there to find this habitable environment. Now, we're not really a life detection mission. That's too ambitious, okay? But we're trying to determine whether or not this ocean underneath, and there's this ice, unfortunately, there's this ice crust. It's maybe 20 kilometers thick or something, maybe 15 miles. We're not sure. We're trying to find that out. We're trying to see if primitive life could exist, if there's a habitable environment here where life could exist, even though we can't detect it. So here we have the heat, we have the smokers, we have a thick icy crust. There probably could be pockets of water in there. But look at the geology here. There may be plumes. Okay, there have been several papers published about plumes on Europa. Now, Enceladus has plumes, and I'll get to that at the end of the talk, but there's definitely active geology. Okay, but the important thing, it has all the ingredients for life. There's water, life as we know it. Okay, essential elements. That's this kind of food, these amino acids and hydrocarbons that Carl Sagan and Bishan Kari and Stanley Miller were cooking in their labs. I mean, even though life didn't we don't think life arose that way, but the food is there that if there are any organisms there, they would have to metabolize. Chemical energy, there has to be some type of energy, and it could be tidal energy. Another thing that's interesting is there are ions. We think there's salt in this ocean, and there are ions. So you have like chemical elements that are exchanging electrons. So you have this electric potential, if you're a chemist, these redox reactions. Okay, but the other thing that's important is it's been stable. We think it's been stable for hundreds of millions, if not a billion years. So that's kind of the view that we want to try and show when we get there. Okay, so I want to leave time for, okay, we're okay. All right, so this is an actual picture. This is an official NASA picture from about 30 years ago when we first started to think about this stuff. And I show this because, it's fanciful, okay? This is the best possible situation. Okay, for starters, you see there's a probe that goes through that ice shell. I mean, we don't have the technology to do that. I mean, even on Earth, looking at organisms underneath pockets of water that are in Antarctica, it's exceedingly difficult to do. Okay, so we really don't have the technology for that. But here's this, why not think about these things? Here's a probe that is actually taking image, because this would really be dark down here, taking images at one of these smokers that might exist on Europa. Okay, so let's go to the surface. I'm not a geologist, but I just want to mention that I am speaking for a very, very large team. When we were building the spacecraft, getting it to Cape Canaveral, to Cape Kennedy for launch, we had about 500 people working on the project. And I want to acknowledge Bob Pappalardo is the project scientist. I'm the deputy, and Haya Korth is a deputy at the Applied Physics Lab, which did provide a lot of the two of the instruments. So I'm not a geologist. I come from an astronomical background. I still observe, and what I'm saying here is just things that I've learned from other geologists. Okay, I have not really done research in this area, but you can see a couple things here really interesting. First of all, there are all these tectonic features called lineae, Line-E, Lin-E-A. I think there's an E at the end there to give the plural. And these are episodic uh, they're episodes on Europa of some type of active geology. We actually haven't seen it happen in the short time we've been observing it, but you can see that in the past there's been phase changes. Ice, as you know, ice when it freezes, it expands. So this could have been, and you have lines going over previous episodes of melting and free freezing. You have these slurries going out onto the surface. Over here, you have it's known as chaotic terrain. Looks like it's come out on the surface. But one of the most interesting things from my point of view is you see different colors, which means different composition. Okay, so some of these dark areas could just be organic material going out onto the surface. We don't know. We have to study that very carefully. Now, one of the things about the surface of Europa, it doesn't have many craters, which means it's a pretty recent surface. About 20 million years, we think, just from counting the craters on it. So it's been active throughout its history. All right, let's see. Okay, here's a close-up of one of these. You can see that these episodes of activity refreezing, they happen. This one kind of went over the sky. I mean, there are several episodes in here of melting and refreezing. Okay, and I don't see a single crater in here. Okay, so let's get onto the spacecraft. How are we going to observe the surface of Europa and try to measure things like the thickness of the crust, the depth of the ocean, and try to understand whether there is active geology? I mean, how do we look for hotspots and things like that? So we have now, this is a sophisticated mission. This is what NASA calls a flagship mission. There are, things like discovery missions that are cheaper. Cassini was the flagship mission. NASA likes to have one mission in the outer solar system, one major mission, one flagship mission in the outer solar system at any given time. So the last one was Cassini, and that's what I kind of worked on. New Horizons, the thing that went to Pluto, that was one class down. Okay, that was a New Frontiers mission. But Europa Clipper is our flagship, our Cadillac mission in the outer solar system. So it's got like 9 or 10 instruments. I did want to talk about it's got a magnetometer. That's kind of bread and butter. You have to measure the magnetic field to tell what the interior is like, see how deep that ocean is. But one thing I wanted to talk about was the solar panels and this newfangled this radar that we have. I mean, past missions I've worked on, we've used the high gain antenna as our radar instrument where we sent out a signal, and then when it came back, we could tell like how high and how rough the surface was and that kind of thing. But when I first came onto this mission, I've only been working on it for about 3 years. I mean, Bob Pappalardo, for example, has been working on it his whole life. Okay, but if you look at these antennas here, I mean, look, this is newfangled. They are just attached to the side of these solar panels. Okay, there's a high frequency. We have like 4 antennas here. Okay, 1, 2, 3, 4. There have been prototypes on the Earth. Okay, we've never flown anything like this in deep space. Okay, and here, this is a very high frequency radar antenna right here. Now, why do we have to have these long antennas? Okay, because the high gain antenna, the wavelength isn't long enough to probe into the ocean underneath the surface. We wanted to see through the ice crust. Okay. These solar panels provide the power. There's no RTGs, these radioisotopic thermal generators. We have solar panels. And that's a really efficient space spin-off. We'll get to that later. We have basically remote, let's see, I think my next, yeah, here's my next slide that shows you the the overview of the instruments. So up above here we have, whoops, okay, so we have these spectrometers. We have a camera. It has a narrow and a wide angle camera. We have a UV spectrometer. We have a thermal imager. Okay, and one of the things is to search for hot spots. If there's some active volcanoes, ice volcanoes, ETHEMIS will be able to find it. We have an IR spectrometer, which is looking for the composition of that red stuff and to see if there's any salt coming out from the surface or the ocean underneath. And then finally we have this really what looked like a scary uh, radar system, but it's deployed and it got really good. When we went by Mars, it took I don't think I have that in this talk, but it did actually get an image of the surface of Mars already. So we've tested it. It looks like it's working. And then so these are all looking down at the nadir, right at the surface of Europa. But then we also have these fields and particles instruments that are kind of sniffing. They're looking for any particles from plumes, trying to understand the atmosphere. So we have a mass spectrometer, a dust analyzer, magnetometer, and then we have a plasma detector. And then also, one of the things I think is the most underappreciated thing, we have all these antennas that are measuring the wobbles on the spacecraft from Europa's gravitational field. And you can deconvolve those and understand the interior of Europa very well. This is, I think, one of the really underappreciated things. Okay, so that's our system. And this is our mission, like condensed into one page. Okay. The science goal is to explore Europa to investigate its habitability. We are not a life detection mission because that's just, as I said before, it's just too ambitious. I mean, what would we look for? Well, we're looking for the three things that you need for life: water, which we're pretty sure is there, chemistry that organisms could use, and then some source of energy to maintain this life. Okay, so we're going to look at the interior, which means to characterize the ice shell. We want to know how deep it is. Does it have salt in it? And any subsurface water, because this ice shell may have pockets of water. And then the ocean underneath, we think it's about 80 kilometers. We'd also like to characterize that and understand how deep it is. Understand the composition, understand the habitability of the ocean through composition and chemistry. Are there organic molecules there? And then just to look at the geology, look for surface features, including sites of recent or current activity, and characterize high interest localities. Here's some high resolution images that Galileo sent back, and you see there's little plates of ice that have cracked more recently than these other striations. And then we're also trying to look for recent activity, such as has been observed in at least a couple occasions by the Hubble Space Telescope, and also by the there's a reanalysis of the magnetic data on Galileo that can be explained in terms of a plume, but there's a paper that just came out literally last week that's a clap back to that says, well, it's unlikely. It's just the atmosphere. So this is how science is, it marches on and you write a paper and then somebody says you're all wrong. So, disagreement drives science. Okay. So this is the instruments being installed in the vault a couple years ago. This is the size of our spacecraft. So this is the space launching system. This is Statue of Liberty. This is 6 stacked school buses. This is the rocket. We were launched on a Falcon Heavy, which SpaceX built. That's a whole other story. Trying to interact with SpaceX when you work for NASA, completely different culture. All right, so here's our spacecraft, and there's a basketball court. So it's about as big as a bat with a solar panels fully extended. And that's the thing, we extended those solar panels like right after launch. And the magnetometer came out right after launch. All these scary things happened right after launch. Okay, okay, so it's about as big as a basketball court. And I did want to talk about these solar panels because they are actually the biggest solar panels in deep space. The Juno spacecraft, which is currently going around Jupiter, but it's a New Frontiers class mission. Like doesn't have all these serious spectrometers and stuff like that. They have solar panels, but it isn't anywhere near as big as ours. And the thing about them is they are much more efficient. I mean, I think so. I did have solar panels on my house before it burned. We had, I think, about 20% efficiency. These are more like 30% efficiency. So I'm hoping that when I have to put these new solar panels on, I can get 30%. This is how, the type of research we do does advance things on Earth here. Okay. By the way, the US didn't build, these were actually built by Airbus in Holland. And we were supposed to put them on at JPL, but we got like behind in schedule. So we had to ship them right to the Cape. And these got put onto the spacecraft at the Cape, at Cape Canaveral. Okay. All right. So I wanted to mention some stuff that was done on the Earth because this is really the radar, this radar system with these long wavelengths, which can peer through the crust of the ice on Europa and get to this possible ocean underneath. Well, we're pretty sure there's an ocean. Um, it it has been tested in Antarctica. Antarctica. The heritage instrument of it has actually been able to um, send radar signals and have this cross section of what this ocean underneath, it's more like a lake. Um, you can actually see the surface here, what it looks like from the data from the heritage instrument to our newfangled radar. Okay. Oh yeah, I did include it. So we fully deployed the radar system at Mars. We went by it on March 1st, 2025. This was really only about, let's see, October, November, December. This was only about 5 or 6 months after launch. The engineers did not want to do this, but we argued, when I say we, it's the science team, the scientists on the mission, argued that we should do it. And the radar was able to actually get these images of Mars successfully. And that was the first time we actually deployed the radar system because you can't deploy it on Earth. I mean, it's so big. So when we deployed it in space and did this end-to-end testing on the radar system. Really cool. Okay. We also got data from ETHEMIS, which is the thermal infrared mapper, and it was able to get heat data. The heritage instrument for that was actually around Mars, still taking some data. So we actually got some data that we could compare and validate that the instrument was working and doing things right. So that was really cool. Okay, the launch. I won't go into the fact that a Category 5 hurricane went over our launch pad on the day we were supposed to launch. This Hurricane Milton, it came out of nowhere. And, I was down there with the rest of the team and staying in a hotel that was hit by a tornado. Because, these hurricanes come up and the squall lines, they have, like, they have these tornadoes at the squall lines when they come up, and this tornado hit our hotel. There were all these buildings destroyed, the launch pad. We had to put it back into the hangar, and the Army Corps of Engineers came and cleaned it all up and got it. We actually launched only 4 days after a Category 5 hurricane. It was really amazing. Okay, so that's kind of it in a nutshell. This little thing that we had to deal with at the last minute. So there's the spacecraft inside the fairing. There are the solar panels. Here it is being taken to legendary Launch Complex 39. Okay, who would have thought that I can remember as a kid going down to Florida and seeing the, Cape Canaveral, and who would know that so many decades later I'd be there launching, as part of the team launching this. Okay, so I do have the obligatory and okay, here it is. Okay, let me see. I'm trying to get some sound in here.
Unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter.
Okay. All right, so here is our mission in a nutshell. So we launched on the 14th. The launch window opened on the 10th of October of 2024. And we launched. And then, as I said, just a mere like 5 months later, we went by Mars. Now, we have to do this thing where you loop in the inner solar system to build up momentum to leave the gravitational force of the sun and make it to Jupiter. Okay. We can't launch directly. We don't have, if we had the SLS, if we had that big rocket that we need, that was behind schedule, we could have gone directly, but we had to use the Falcon Heavy, and that doesn't have the thrust to get us out to Jupiter on a direct orbit. So we had to do this thing where you go into the inner solar system, you pick up momentum from the planets. So Mars Gravity Assist, and now we're doing an Earth flyby on December 3rd of this year. Okay, and we're actually getting ready to do that, and that's where I'm going to talk about the observer's opportunity. Okay, coming in, going by Earth. And by the way, we're going to really be exercising our instruments at Earth. The thing at Mars was we had to fight to get it, but it was so useful in validating the instruments that they can work and everything that we're going to do a full, like, not a full Europa flyby, but it's going to be most of the instruments are going to be working. So let's see. Here's our mission. I want to save time for questions, okay? But I do wanted to, and this is the only eye chart I have, and I put this up, just to show you that it is really complex. It really is rocket science. We have 49 flybys of Europa. We are actually not orbiting Europa. We're orbiting Jupiter. Why are we doing that? Because of the radiation environment. The radiation environment in Jupiter is it's brutal. There's a lot of charged particles. We have sensitive electronics. We want to preserve them. So we only swoop in to the inner part of the system, to Europa, for a short period of time. This is our closest approach. This is where we get most of our observations. We have 49 of these orbits in the nominal plan. And this is just to show how complicated it is. We have a bulk data system. That's where we put our data. The Deep Space Network starts to read some of it down, post and sell it. We have some bias. We have to measure the orbit and then do a cleanup maneuver and do some calibrations. And then one of the instruments has to do a calibration here. We have to do a targeting maneuver, read some more of the data back. So it's really complex. Okay. So that's why I put that up to get across an appreciation for the complexity. Okay. But these 49 orbits, we are going to map Europa quite closely. We're even getting to the poles here, which we haven't seen very well. A lot of it is on the equator. We have a lot of targets. Like here's one of the few craters on Europa, Quill. We're going to try to get that observed. The puddle, I think that's one of the chaotic terrains. Let's see, Thrace is chaotic terrain. So we're trying to basically cover the surface, and the close approaches, they approach like 25 or 35 kilometers. And some of them are far out where you can kind of get a bird's eye view. Okay. So there are more ocean worlds than Enceladus. I'm sorry, than Europa. Okay, Europa is the first one we're going to study in detail. But we already know that Enceladus, this moon of Saturn, uh, has an ocean. Whether it's global or not is controversial, but it had active plumes. Triton, which is a moon of Neptune, has active geology on it, but it seems to be surface geology. It's just like there are plumes coming from a polar cap. Titan, now it has liquid on the surface, but it's hydrocarbon. It's ethane and methane. It's not water. I mean, water is like a rock out there, but it seems to have a water ocean. Ganymede probably does. Callisto may. Ceres has this crater called Akator that is spewing out uh, OH, the OH molecule. So there's some kind of or the OH radical. So there's some kind of a pocket of water in there. Pluto, the New Horizons spacecraft flew by it. It didn't get enough data to understand its interior. Okay, but Pluto may have an ocean underneath as well. And of course, our own Earth is an ocean world with lots of water on the surface. So fragile and so precious that we have to preserve it. Let's see. I did want to end with, NASA loves to give out some of, Earthling's gifts whenever it sends a spacecraft out into the solar system. Now, this was started, I think there was a plaque, I was talking about this for a group of engineers, I think, and they pointed out to me that there were some things on the Pioneer spacecraft as well. Okay, but the first thing that I'm really familiar with is the Voyager record, because when I was at Cornell, this is when Carl Sagan was kind of, advertising this, and he wrote a book about it, and he signed it, and I lost it in the fire. But anyway, so here is the golden record, and I mean Voyager is now out past. They're both past the solar system. They're out in the galaxy. Is it, I think, 150 light 15 or 150 light years? I'm sorry, can't make that mistake. AUs, okay. We still are watching it. There's still Linda Spilker is the project scientist, and she's still working at JPL. Ed Stone, of course, was a project scientist, and he passed away. But we're still okay. So we're still monitoring it with a deep space network. Here are the images that were on that record. Okay, and like for example, this one here. This is Val Boryakov, who was at Cornell then. He's passed away. This is George Halou. He was my office mate, and he still actually works at Caltech and IPAC. And this is Wendy Gradison. I don't know where she ended up, but I knew some of the people that were photographed in this. But here is the plaque that we sent out. Okay, was put together before I came on the project, but you'll notice here is the Drake equation. Okay. The daughter of Frank Drake, who's a noted science journalist, wanted to send some of his ashes into space. Okay, this is a whole other story. There's so many interesting things here. But NASA said, no, we're not doing that anymore. Because, Clyde Tombaugh had a little uh, canister with some of his ashes in that was on the New Horizons spacecraft. And it was done secretly, and NASA didn't know about it, and they got angry about it. So they said, okay, when I say NASA, I mean NASA headquarters, because we're NASA too, but this is NASA headquarters. This is just, we're not sending people's ashes out into space. We don't care who they are. So instead, we actually wrote the Drake equation on there, and I'm sure everybody in the audience knows what that is. Then we had this thing called Message in a Bottle that had the names of over 2 million Earthlings that signed on to this poem that was written just for us by the poet laureate. We had the U.S. poet laureate, Ada Limon. We had a little partnership with her in the Library of Congress. So we had this little, it's not shown on here, but there's a little chip there with all these names on. And this was Ron Greeley, who was one of the early pioneers in advocating for this mission. He was Bob Papalardo's thesis advisor, and he also died. He died before his time. I mean, so many of these people, Carl Sagan was only like 62 when he died, but he died before his time. He just dropped dead from a heart attack. He was a workaholic, and we wanted to just have that little picture of him. But on the So this is on the side that's on the spacecraft, and on the side that faces us, this is a waveform for water in over 100 languages. Okay. So I'm going to end this. I can take some questions, but I do want to end this by reading Ada Limon's poem. In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water, each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark. So that's what's going onto our spacecraft. And you're probably going to ask me, what is the disposal scenario for the Europa Clipper? I mean, we're not going out, into outer space. We're not going to 100 or 150 AUs. We're going to crash into Ganymede. That's how we're going to end up. But still, this poem, and actually, I noticed if you go online, you can actually hear Ada Limon saying it. And she was at the launch and she really engaged with us. She came out to see the spacecraft it was a really good partnership with the Library of Congress and the Poet Laureate. Thank you for having me. Yeah, great club, great astronomy club you've got. Yeah, thank you so much.